Let's discuss the properties of the derivative of vector-valued functions. Let R and U be differentiable vector-valued functions of t. Let f be a differentiable real-valued function of t. This is a real function, and R and U are vector functions. And let C be a scalar. Now, the derivative of a scalar multiplied by a vector function is equal to the scalar multiplied by the derivative of the vector function r. Now, if we have two vector functions added or subtracted, the derivative of r and u is the derivative of r plus or minus the derivative of u. If we have a real function multiplied by a vector function, their derivative is equal to the derivative of the real times vector function plus the derivative of the real times the derivative of the vector function, similar to the u times v. U times v is equal to u prime. This is the derivative formula we memorized in the from the previous courses, that the derivative of u dot v is equal to u prime v time u prime times v plus v prime times u. If we have the derivative of the dot product of two vector functions, it's also the same as this formula. It is u prime v plus v prime u. If we have the cross product of two vector functions, the derivative of this cross product is equal to r prime times cross u plus r cross u prime. Okay, what if we have a composite function? The derivative of a composite function, um, the composite function is usually written as r is composed with f. This is how it is written. R is composed with f is equal to r of f of t. This is the definition of a composite function. You replace f in r. Now we want to do the derivative of a composite function. So the first thing you need to do before doing the derivative of r, first of all, replace f in r. Then you do the derivative of r. So this is the derivative of r of f of t times the derivative of the real function, or the derivative of f. If you have r dot t, r of t dot r of t equal to constant, then the derivative, then r dot r prime is equal to 0. Let me explain this in more detail. What does that mean? So we have r dot r equal to c. This means that r dot r prime is equal to 0. Now, if we have the derivative, let's do the derivative of this one. The derivative of r dot r is equal to c, since the dot product of two vectors gives you a constant, c, a scalar. So when we're doing the derivative on the left side, we're going to do the derivative on the right side. Okay, the derivative of r dot r, again, the derivative of u dot v will give you u prime v plus v prime u. This is the derivative. This is the definition of whenever you have the derivative of u and v, this is the formula, u prime v plus v prime u. So again, we have this one and we have r prime dot r plus r dot r prime. We know that from the property of whenever we have dot product, and that we know that the dot product is commutative, which means that r prime dot r is equal to r dot r prime. We can rearrange it, and the order of the dot product is not important. We saw this from the previous lecture when we discussed the properties of dot products, and we said that the order is not important, and you can put R prime the first or the second, it doesn't matter. While for the cross product, the order in the cross product is important. So since the order is not important, we can add these two together, and you will gonna get 2 times R dot R prime, which is equal to 0. It is equal to 0 because the derivative of a constant is equal to 0. Now, cross multiply to get rid of 2, you're going to get r dot r prime is equal to 0. What does that mean from the definition over here? What does that mean? This means if you do the dot product of two vectors and gives you 0, this means that the two vectors are perpendicular. So this means that r is perpendicular to r prime. R gives you the vector function which we plotted last time. It shows you the position of uh, the R vector at a particular point in space at t. So this is R, and the derivative is perpendicular to R, and its derivative is R prime. This means r dot r is equal to 0. This means that r is perpendicular to r prime, or the derivative of the vector function is perpendicular to its vector function. And in physics, when you have a trajectory r going a path of an object going in this direction, and r gives us the information on how this object is moving in space, doing the derivative of r gives you the velocity. The velocity, this is the velocity of this object in space. And this velocity vector, this is also a vector, and this is also a vector. The velocity in space is perpendicular to its trajectory r. In example 3.6, we're going to use the properties of the derivatives of vector function. We have this vector function r and another vector function u, and in part A we want to calculate the derivative of the dot product of r and u, and in part B we want to calculate the derivative of the cross product of u and u prime with respect to t. Let's start with part A, the dot product. First of all, we have R and we have U. And according to the properties we started before, we're gonna use this one, the derivative of the dot product, which is U prime V plus V prime U. And we are gonna apply this formula over here. The first thing we need to do is to do the derivative of R. So the derivative of R is this one. Go ahead, please, and do the derivative of R, and you're gonna get this one. If you have problems with doing the derivative, please let me know. And dot u, this is u. You don't do anything for u, you just write it again. We have the plus over here, we write the plus, and r, we write r, which is given in part A, and then u prime, you do the derivative of u. This is u prime. This is the derivative of this one. Now, we have dot product. We need to evaluate this one. Let's start with the first dot product. x component will be multiplied by the x component of this vector, which means 6 times t squared minus 3. So this is the first one. This is the first x component multiplied by x component of the second vector. Now the y component of the first vector multiplied by the second component of the y component of the second vector. So this is it. And again 5 times t cubed minus 3t, this is 1. And for the second one, you do the same. You multiply the x component with the x component, the y component with the y component, and the z component with the z component, and you're gonna get this one. You add them, and you get this result, which is the derivative of the dot product of these two vectors with respect to t. Now, the cross product, be careful that we're not finding the cross product between r and u. We're finding the cross product between the vector function u and its derivative. Okay, again, we use the same formula we used for this one, this u prime v plus v prime u, and let's find the derivative, the double derivative, u double prime. U double prime is the derivative of u prime, which means that we already did the derivative of u prime. This is it. This is u prime. We're gonna do the derivative also for this one to get u double prime. And the double derivative of u is equal to 2i plus 6t. Okay, now let's look at the first term. We know that if we have the cross product of the same vector, like r cross r, these are vectors, is equal to a zero vector. So whenever we're doing the cross product of the same vector, you're gonna get zero vector. So u prime cross u prime will give you 0. Now we want to evaluate the second term. So the first one is 0, and we want to find the vector, the cross product of u and u double prime. To evaluate this, we're gonna put them in a determinant. The first row will be I, j, and k. The second row will be our first vector u, and this is our second vector, which is u double prime. And since we don't have j here, j unit vector, the y component is 0. Expand this one, evaluate, and you're gonna get the result for this cross product. And this will be the derivative with respect to t for the cross product between u and u prime. Now let's discuss tangent vectors. Recall that the derivative at a point can be interpreted as the slope of the tangent line to the graph at this point, which we discussed when we recalled the basic ideas of the derivatives. In the case of vector valued function, the derivative provides a tangent vector to the curve represented by the function. We also discussed this, that it is perpendicular to the vector. The derivative is always perpendicular to its vector valued function. So if we have a vector function given by r, the derivative of this function r prime will be perpendicular to r. And let's say that this is an example, and let's say that we're interested to find it at t equal to pi over 6. Replace pi over 6 in both to find r of pi of 6 and r prime of pi over 6. And you're gonna get these ones. And if you plot these ones, you're gonna get this graph. First of all, if you plot this vector function, you're gonna get a circle of radius 1, and it's circulating in this direction because this is the positive direction, as you can see from this arrow over here, it's moving counterclockwise. And if you find r of pi over 6, this will be a vector pointing in this direction, and this is r of pi over 6. It is a point at this circle over here. And if you plot this vector now, r prime, at this point at pi over 6, you're gonna get this vector. You can try it out and you're gonna get the blue color vector. And this one is perpendicular to r. Now let's discuss unit tangent vectors. We now understand tangent vectors and how we can get them for vector functions, and they are perpendicular. Now we are interested to find the unit vector of this tangent vector. And we know that the unit vector will be it will be parallel to its vector and pointing in the same direction. So the unit vector will give us information about the direction of this tangent line. Let C be a curve defined by a vector function r, and assume that r prime exists. We don't have any problems when we do the derivative. It's always defined, and also it's defined at this point t equal to 0, to naught. Vector r prime of t naught, so we've done the derivative and we replace t equal to 0. So it will give us a tangent vector at a point t equal to t naught, as we saw now. So the tangent, the principal unit tangent vector, to calculate this unit vector or unit tangent vector, we will denote it as t equal to r prime of t. This is the derivative of r divided by the magnitude of the derivative. You are familiar with this formula. It is similar to the formula, the one that we use to find the unit vector of any vector in the first chapter. Of course, r prime cannot be equal to 0 because we cannot divide by 0. It will be undefined. So this is a condition imposed to this relation. Okay, in this example, we're gonna find the unit tangent vector. We have a vector r cosine t I plus sine t j, and we want to find the unit tangent vector. This is easy because according to the formula, you have to find the derivative of r and then its magnitude. The first step is to find the derivative of r. The derivative of cosine t is minus sine t, and the derivative of sine t is cosine t. And the magnitude now, it is the square root of the square of the x component plus the square of the y component. Sine squared t plus cosine squared t is equal to 1, and radical 1 is equal to 1. Now, let's replace these in this formula. The magnitude is equal to 1, and this is r prime, and the result will be minus sine ti plus cosine tj, and this is the tangent unit vector. For the second part, u, we will apply the same steps, and this is given, u is given, and we do the derivative of each component individually, and you will get 6t plus 2i minus 12t squared j and 6k. Now, its magnitude, we do the same. We have a third component, the z component, because this is a three-dimensional vector function. So don't forget, whenever you're taking the square root of the square of the x component plus the square of the y component, please add the square of the z component as well, which is 6 squared in this case. Square all the terms and add them, and you're gonna get this one. Now let's divide u prime and the magnitude of u prime, and you will get this one. This would be the tangent unit vector. We can further simplify it by simplifying 2, which each component in the numerator over here. And this is the final form, and this is the tangent unit vector. Finally, in section 3.2, we will discuss integral of vector valued functions. Let g, f, g, and h be real functions that you can integrate over a closed interval a and b. We will consider two cases, a two-dimensional vector function r and a three-dimensional vector. When we integrate r, you will integrate each component individually, the x component and the y component. This is the indefinite integral. For a definite integral, where we have a definite uh, uh, closed interval where you're gonna replace the lower bound a and the upper bound a. These are the limits of known as the limits of integration. You will apply the same rule as this one. You will integrate, take the definite integral of the x component and the y component individually. This also applies for a function with the three-dimensional case, where you also do the integration, the definite and the indefinite and the definite integration for each component individually. When you're doing the indefinite, please note, when you're doing the indefinite integral, for example, of this one, f of t, and you get the antiderivative of f, you use to add a constant. This is a real function, not a vector function. As you can see here, if you integrate a real function, you're gonna get the antiderivative of this real function. Yes, and you use to add a constant at the end of the result. This also should be done for the vector integration. So when you're doing this integration, let's say you got the antiderivative f of, this is the antiderivative of f, and you add a constant of integration over here, c1. And this is also the case when you're doing the integration of a real function. You're going to add another constant after the integration C2. Now, group C1 and C2 together over here, and we will call C1I plus C2J equal to C. And if you realize that, you will realize that C over here is a vector. C1 over here and C2 are scalars. C is a vector, which is equal to C1I. C1 is the x component of this vector, and C2 is the y component of this vector. Like this. When we're writing them, this is by handwriting. We're adding the hats and the vector. The hats for the unit vectors and the vector, the arrow for the vector to indicate this is a vector. So C is the integration constants that is also a constant vector. You can draw this vector actually because you already have the x and y components. Let's take an example. And in example 3.8, we will do a definite integration for this vector function. The first thing to do is to take each one alone, and you're going to do the integration for each component individually. This is the integration for the x, y, and z components. Whenever you're doing the integration of a variable to a power like this, we have a variable tn, the integration of this one, the integration is equal to t plus, to the power of n plus 1, you add 1 to the power and you divide it by n plus 1. For example, the integration of 3t squared is 3t 2 plus 1, which is 3, divided by also 2 plus 1, which is 3. Now we can divide 3 divided by 3 is equal to 1, and you will get t cubed. Do the same for the others. Apply this integration rule for each one, for 2t, for 3t, for 6, 6t cubed, 5t squared, and minus 4. You're gonna get this vector. Don't forget to add plus the integration constant plus c, and this is a vector. Don't forget to put a vector for c. Now for the second part, you have the integration of two vectors. They are given in component form, okay, not in a linear combination form. And in component form, we're gonna do the cross product. First of all, before doing the integration, evaluate the cross product, then do the integration. You have these two vectors. Let's evaluate the cross product. First of all, we will use the determinant rule. And in the first row, the I, J, K unit vectors. The second row will be the first vector, and the third row will be our second vector. Expand, evaluate this determinant. We've done this lot in the previous chapter, and you're gonna get this vector. Now let's integrate it. Let's integrate. You integrate, you apply the same integration rule, this formula, to these components, and you're gonna get this one. Don't forget to add the integration constant at the end after every definite integral. The third part, C, we have a definite integral. This is the lower bound and this is the upper bound. These are the limits of integration. So first, let's integrate, and then we will replace these values after doing the integrations. Okay, the first thing we need to do is to integrate each component alone. Okay, the first one is sine 2t. We want to integrate sine 2t. We know from before that the integration of sine ax, where a here is a scalar, is a constant, and if we do the integration of sine ax with respect to x or dx, it is equal to minus 1 over a cosine ax. So let's apply this formula. In this case, a is 2. This will give you minus 1 over 2, and cosine, this formula tells you you take the cosine ax, the cosine, which means the cosine 2t. You do, in the definite integrals, you don't put the constant of integration. You don't do that, okay? So we will then replace pi over 3 and 0 in cosine t. The integration of tangent t is given by this formula. The integration of tangent ax is minus 1 over a ln, which is a function, it's a natural log function, ln of cosine ax. Let's apply this formula. Let's use it. So a is here 1, 1. So we will have 1 divided by 1, which is 1. So we will have minus 1 over here times ln, the cosine of t. And lastly, you know how to calculate a variable, having a variable with a power, and the integration of e to the power of minus t is half e to the power of minus t. Now, all you have to do is to replace pi over 3 in the cosine, and then you minus this one, and then you replace 0. Since minus times minus is positive, we're gonna write positive half cosine and replace 0 in the cosine. Also do the same for the y component over here. Replace pi over 2 in the ln cosine pi over 2 minus, replace now 0, you will have ln cosine 0. Same thing for the z component. You evaluate, calculate, and you're gonna get the final result is this one.